Hi guys. Now cases on dielectrics. We have discussed about two cases in previous class. Now here we will discuss case third. Case third is if a parallel plates capacitor is filled by a number of dielectrics of dielectric constant K1, K2, K3 up to Kn having thickness x1, x2, x3 up to xn. Then we have to find that how much is the parallel plate capacitor and its magnitude. Then simply here we are going to draw a diagram. See, this one is a parallel plate capacitor having terminals. Suppose this terminal is connected with a positive potential and this one with negative potential. Now we have to insert, there is number of dielectrics between these parallel plates. So you just insert number of dielectrics. Each dielectrics having dielectric constant you supposed to be K1, K2 and K3, and this one having some thickness its thickness you just supposed to be that this one is x1, x2 and x3, where the space between these two parallel plates be d. So you just use the previous concept from case 1, and from case 1 your previous concept is that C is equal to epsilon naught A by D minus X plus X by K. This is a common relation from case 1. So we have to use this relation for this case. So now for this case your capacitance that will be epsilon naught A, where A is the area of this parallel plate. So its area be A and the space between these two parallel plates be B. So there will be epsilon naught A divided by D minus, in place of X there will be number of dielectrics having thickness x1, x2, x3, and now one last one is be there. This one is xn. So its thickness be xn and its dielectric constant be xn. So we just use the number of thickness that is x1 minus x2 minus x3 minus up to, you have to go up to xn. So minus xn plus x by k. So there will be x1 by k1 plus x2 by k2 plus x3 by k3 plus up to plus xn by kn. So this one is your resultant. So now you can use this one for number of dielectrics, that epsilon naught A by this much. So this one is your capacitance. In next case, case 4, suppose if you want to fill this gap by using a conducting slab, but that would be also I wanted to fill partially. So now case 4 is that if a parallel plates capacitor is partially filled by a conducting slab of dielectrics constant infinite. You know that the dielectric constant of a conducting slab is always infinite. We have studied earlier. Having thickness x. So from here we will again use this concept. So this one is your major concept and primary concept that you have to remember for each case. That's why here I would like to keep only one dielectric slab. So suppose this one is a conducting slab, and we know that conducting slab having dielectric constant infinite and its thickness be x, having x thickness, and the space between the parallel plates be d. So the rest space between the plates be d minus x, this much. But right now we will use this common concept and we apply this in this common concept from here. So accordingly Accordingly, now use this primary concept that C is equal to epsilon naught A. So this one is epsilon naught A by D. So in place of D, the net space will be, so D will be there. And now your conducting slab having thickness X plus X by, in place of K you just put it infinite. So what happens from here, that C is equal to simple epsilon naught A divided by D minus X. Why D minus X? Because X by infinite be 0. Because something by infinite will be always 0, because infinite is 1 by 0. So denominator of denominator is 0. That comes in numerator. So 0 by something will be 0. Therefore you will get only D minus X. Right now, this one is your resultant. But one more case is that if this space is fully filled by this conducting slab, then what happens to your capacitor? Now see, so we can see this one in another case, case 5. So in this case 5, if a parallel plate's capacitor is fully, not partially, this one is fully filled by a conducting slab of dielectric constant infinite same having thickness D, because it is fully filled by conducting slab. So right now we are going to fill the full slab, the full space by this conducting slab. So here is infinite dielectric constant. Same result we have to use in this primary case. So accordingly you have to put here epsilon naught A, this one is same. In place of D, D is there. In place of X, this is your fully D. Here X is equal to D, because whole empty space is filled by conducting slab. That's why you can replace from here that in place of X just put D, plus in place of X put D and divided by infinite. So what you will get from here, you can see that C is equal to epsilon naught A, we remain at there. Now D minus D is 0, and again this one will be cancelled, and again D by infinite. So something by infinite will 0, and now something by 0, this will be infinite. So your capacitance will be infinite. So your capacitance will be infinite. Now you can use another way to find the capacitance. If you don't want to use this primary concept, so simply you can use this concept, because you know the capacitance of a dielectric. If a dielectric is fully filled between a parallel plate capacitance, so there is a concept that C is equal to K times epsilon naught A by D. So what you have to take? You have to take the value of dielectric. So you know that you are going to be put in place of dielectric, there is a conducting slab having dielectric constant infinite. So you just put there. So infinite multiplied by anything will infinite. So you will get same result, infinite there also.